when I started looking at, okay, well, what does it take to get this ready to go to the moon? How do you get this stuff and get it to TRL level 6, which is relevant environment testing, before you send it to space? There weren't a lot of test facilities available that people could go and test their stuff. There's some sandboxes here and there with Lunar Regolith simulant, but not in vacuum, and you couldn't do the temperature simulations, and you can't do the temperature day-night cycles, or they're really small, and so you could only test like a small piece of it. Or NASA has some really giant ones, but obviously it's like $1 million a test, so that's certainly not affordable for startup companies or for universities. And so what I thought there was going to be a need for was a test capability for CLPS-sized systems, right? The CLPS is in the commercial lunar payload services systems. Commercial companies can send cargo to the lunar surface. And so a lot of companies are developing these payloads, but where can you test them? And so the idea of the Planetary Surface Technology Development Test Lab is that we can do a bunch of that testing. And so we can develop the payloads. We have an 1,100 square foot lab where we can go from initial prototyping, 3D printing, just quick iterations, to a sandbox that we have in the lab that is filled with Lunar Regolith simulant, where we can do, it's a 14-foot by 6-foot box, where we can drive around and get some more experience in actually driving this thing around, look at traction. In the future, we can do some gravity offloading, so we can simulate 1/6 gravity by lifting up 5/6 of the weight, and so it only has 1/6 of the weight left on the wheels, basically, so you can look at the traction. And then the next step, right, once you sort of got your design sort of, oh yeah, we think this is pretty good, now you can start doing your space quality testing. And so now you can start simulating the vacuum, the temperatures, and of course the Regolith simulant under vacuum conditions.
We're back with another episode of the Cold Star Project. I am Jason Kanigan, your host, and I'm here with Dr. Paul Van Susante. He is assistant professor in the mechanical engineering and mechanics department at Michigan Technological University. And you also have a connection with the Colorado School of Mines, which I was very pleased to see when I first came across that. Thanks for being here.
Thanks, Jason. Glad to be here. It's fun. I always call myself a graduate of the Space Resources Program before it existed.
Right. Well, yeah, I mean, your PhD is in engineering systems from the Colorado School of Mines. So you spent a fair amount of time there, some years. You've been involved in, I'm reading this off this other screen here, Lunar and Mars construction and in situ resource utilization for 20 years. So you've been investigator or co-investigator of a number of studies of like, how are we actually going to do this stuff? And when I first ran into you online, you were getting into building test beds and getting stuff together. And then all that has gone out the window for the short term here, which kind of makes things a little crazy. But let's begin with this. Quite a few scientists are investigating the properties of the Lunar Regolith, and what can we do about ISRU and building stuff when we get there. What properties and results have you been focusing on?
Well, one of the important parts when you deal with Lunar Regolith is that it behaves very differently than dirt on this planet here, right? And so when you're trying to design machines that are going to have to operate on other planetary surfaces, whether that's the moon or Mars or asteroids, whatever, you can't just pick up sand here and say, hey, this is going to behave the same way. And so we have to really take into account how it behaves differently and what the critical pieces of that are. And so for the moon, one of the critical aspects of that are the particle sizes, because it's very fine material, and then particle shapes, because particle shapes determine how well things interlock, for instance. And so you can basically make a vertical wall out of lunar dust. In its position as it is now. Once you dig it up, you loosen it up, and then that doesn't happen. But to me, that's one of the critical pieces, because one of the things that I work on is designing robots to work in that material, right? And so moving it, digging it up, and driving on it, and all sorts sort of thing is greatly determined by the particle shapes and sizes. And then, a secondary effect of that, of course, is how does it affect the machine? So how abrasive is it? How much scratches does it have? One of the things few people know about is that during the Apollo extravehicular activities, so when the Apollo astronauts are in the spacesuit out on the surface, after 3 of those excursions outside of their vehicle, the seals had degraded by about 80%. And what that means is that they may have been able to do one more excursion outside of their vehicle before the seals would essentially fail, and they could not create a pressurized envelope in their spacesuit anymore, right? And so that's 4 times,
right,
in 4 days, basically. And so, if you talk about, we're going to mine the moon and we're going to have to work in this stuff for years on end without maintenance, that's a little bit of a discrepancy there. That's a challenge that we have to figure out, right? That's the kind of stuff we're interested in.
Right. Yeah, and this is fascinating to me. It goes back to even my World War II studies, where the German tank builders built these beautiful, expensive, highly tuned war machines, and then after knocking France out, sent them east into Russia, and the Soviet Union was full of dirt roads. And all that dust defeated these panzers. It just clogged up the transmissions, and it knocked the tanks out. They couldn't fight. So, this is not just a terrible thing on the moon. It's bad enough on Earth too, and then you add it. So something that I've heard you talk about today that I haven't heard before from other folks that I've encountered in this area is the discussion of the shape of these things, these particulate and that on the moon. Could you go into that a little bit and describe for our audience who probably hasn't really heard of or thought about this stuff at all, what that is like?
All right. So lunar regolith, which basically means the broken up top layer of the surface of the moon, is what the difference the main difference is how it was formed, right? So here on Earth we have lots of processes that blow the dirt around, and water that rolls the stuff around. I imagine you're on the beach and the wave action, right? So it keeps moving the particles back and forth, and so all the particles here on Earth, by wind or water, typically get rounded over time. And that does not happen on the moon. There is no wind, there's no water. And so one of the things that happens on the moon that doesn't happen so much here on Earth is the meteorite impacts, right? So there's constant bombardment for billions of years of small grains and even molecules that just keep bombarding the surface. And so the lunar surface gets broken up into very small pieces over time. And you can imagine that it gets broken and then it doesn't roll around, so that you get sharp edges because of that. But not only that, because of those micrometeorite impacts, you also get local melts happening. So because of the impact, because it's really high velocities, like 20 kilometers per second or something like that, they impact lunar soil, and then locally you get a small impact crater, and you get some melted material that then splashes onto other things.
Right.
And so I don't know if you've ever been in Hawaii and walked on the lava fields, but that's extremely sharp basalt glass almost, right? And so it's kind of like that, except really small.
Right.
And so it's like glass shards in a way.
Right. I had some fun on Wikipedia checking that stuff out. It's little, almost turd-sized glass little things. They're brown and sharp, like you say. I was going to include that in an Ask Professor Astronaut episode at some point, I think, because they can be made funny quite quickly. But there's nothing funny about them when you're trying to, work around them or with them on the moon there. So, tell us a little bit about projects that you've worked so far on. You've gotten funding. You've had to go get NASA support and that create some things.
Yeah. So basically how this all got started is that I was a design engineer, right? And so we did a lot of paper projects, and we started designing things, and everything looks great on paper and on the computer, But then I was thinking, like, oh yeah, great, this telescope. We did some designs for telescopes on the moon, and it's like, okay, great. Now, how are you going to build this thing? And so how do you put it in place? What kind of equipment do you actually need to build something like that? How do you make a road? And you can't just go to a Caterpillar dealer and then, get one and then it works, right? So the question is, how do you actually design a machine that can do these kinds of cool things that will bring us to the next step, which is, making constructions on the moon, and then come up with these things like telescopes or lunar bases or mining. But first you got to have that equipment. And so what does that look like? And so I started making simple prototypes, like senior design project type things for maybe $2,000-3,000. And it's like, okay, let's just build a backhoe and see how that works. So let's build a bucket excavator and see how that works. And so from that, we built up quite a bit of experience in, working with these kinds of things, figuring out what might work, what might not work, what's a promising thing from a mass and energy use standpoint, and then further develop it to the point where you might actually start being able to use it in a vacuum. And so from a project standpoint, right, so there was always a funding question, right? So the question is, who will pay for the development of this technology? And so NASA has some interesting programs that specifically focus on technology development. And so the goal of those programs is to get it from the idea to, in the end, TRL level 6, technology readiness level, where you have tested that equipment in a relevant environment. And so that would mean, in this case, vacuum with the lunar simulant, and preferably to the temperatures that you will encounter on the lunar surface. And so those programs, there's a variety of different programs. There are like things like small business innovative research grants. There are broad agency announcements. There are things like early stage innovation grants, and then there are other programs that are specifically focused on universities. And so each of those programs focuses on specific portions of that TRL spectrum. SBIRs are typically, low TRLs. Early stage innovation is even earlier, maybe 1 to 4. And then other programs focus more on the later side, so get it to TRL level 6. And so I've participated in several of those kinds of programs. I've worked with partners like Honeybee Robotics, several NASA centers, and some other small companies to get grants and then to develop different technologies. I've worked on building landing pads. Like, how do you pick up rocks? Can you use rocks to build a landing pad? Simulations of that, as well as testing it out and testing what kind of connections you can create. We have a grant right now for what's called early stage innovation to mine water from gypsum on Mars. Then we have another grant together with Honeybee Robotics that's looking at buried glaciers on Mars, and how can you access those buried glaciers and then melt the ice directly and then pump that up. And then I'm involved with CLASS, which is a NASA Virtual Institute, Center for Lunar and Asteroid Surface Science. And the idea there is that there's a variety of different approaches of scientists working together to, in this case, also study variety of different aspects. And my focus is then the local use of materials. And so for landing pads, but also for extracting water. And my focus is not so much the chemistry side, but mostly the robotics side. And how do you actually design a machine that would then, let's say, pick up a rock and sort them out to different sizes and put them in place? Or how do you actually pick up the lunar dust to extract the oxygen from it? Or, if there is ice, how to actually mine that ice with a machine.
Right. And this stuff terrestrially sounds fairly straightforward, but you've got to build something that can handle the vibration of launch and getting there, and then maybe has to unfold itself or be put together. You have to have a landing place for it. If you bring something down as an initial lander and then another thing comes down to land additional parts, that's going to blow dust everywhere. And we've already talked about that fast degradation of seals. So there are serious problems here of even touching this stuff and trying to work with it. Makes your machinery less functional. So I am fascinated with this and how it's going to get figured out, because it's just not that simple. So you founded something called the Mining Innovation Enterprise, or MINE. What is it and what does it do?
So I'm an assistant professor here at Michigan Tech. And so at Michigan Tech, we have a program which is called the Enterprise Program. And most people are familiar with capstone design, senior design. And Enterprise is a little bit different in the sense that it allows you, or I should say, it allows students to be involved for projects for multiple years. And so the Mining Innovation Enterprise that I founded 5 years ago had as a goal to come up with innovative ways to do mining. And it's not limited to space mining. That's one aspect of it. So we also have a team looking at underwater mining, and we have collaborated with some mining companies about design of above ground and underground mines as well. But the idea is that the students can get involved basically from their sophomore year, basically, until they're seniors. So for 3 years, if they want to, and they can also just do multi-year projects. So instead of doing a project only 2 semesters, you could work on the same project for 3 years if you wanted to. And so the Mining Innovation Enterprise currently has about 30 students that are involved with a variety of different projects. Like I said, one is underwater mining. One is the Lunabotics Mining Competition, which is a NASA competition for college students, kind of a college version of FIRST Robotics, if you will. But in this case, to build a robot that can autonomously traverse over an obstacle zone, which has lunar simulant, craters, and rocks, and then go to an excavation zone, dig down about a foot of Lunar Regolith simulant, so more the dusty kind, and then find the rocks. The rocks underneath that 30 centimeters are intended to simulate the ice chunks. And then so we have to collect those ice chunks and then again autonomously traverse back over the obstacle zone back to the lander, right? We're simulating a lunar mission, and then dump those ice rocks into the processing unit in this case. Right, and so that's one of the projects we do, and then the other students are helping out with the research that's going on. So a lot of the graduate students do a lot of the research, but then the undergraduates get the experience as well to help out with these research projects. For instance, the gypsum processing unit, or designing an excavator that then goes in my simulant sandbox to then test how it behaves with the Lunabotics rover or with the trencher or some other kind of hardware that we're building. So,
okay, yeah, this is really interesting. Do you find, I've talked with other professors at other universities, and in the satellite world, it's very good to partner up experienced students with new students so that there's that knowledge transfer. Does this happen the same way in the robotics field, or is it a little different?
No, that's similar. So one of the challenges with senior design, like when I used to run a Lunabotics team as a senior design project, and so the students do that project for 2 semesters and then they graduate, right? They're gone. And so the lessons learned from that team disappear with the students, basically, right? Yeah, well, I remember them, but like
right.
The students are like, yeah, my mom told me, this,
right.
so I'm not going to listen to you, right? So the experience of doing this and learning from what happens is invaluable, and reading it out of a book or me telling them is just not the same kind of learning experience than being involved for multiple years and transferring that knowledge by experience in a way. And so the enterprise program is fairly unique in the country, actually, and so it does allow that multi-year learning. And so a lot of our senior students sort of get more of a management of experience of helping the younger students to do the technical work and then learn those lessons along the way before they then have to perform it themselves. And so it's a quick maturation and sort of institutional memory of these projects that really helps, that multi-year cycle really helps to avoid that, all the experience just left, and now we got to start from scratch.
Right. Well, I'm glad to hear that, and that it's like a deliberate part of the thing that you're organizing, because that's important out in the commercial world as well. We see that institutional knowledge disappearing very quickly, and yeah, once they're gone, it's not like you're going to be able to get them back and sit them in front of a video camera to do an interview or something like that, and they're sure not going to write you. So, yeah. It is really important. So is that a shirt for the MINE program?
Yes, it is.
I see it. I just noticed that. Yeah, yeah. Very cool. All right. Now, I'm just thinking about the components for the robotic experiments that you're doing. With small sats, you can buy stuff off the shelf. It's still not that great, and it needs to be tested and that. Do you find you have to make your own stuff to handle these tolerances and this environment?
Yes and no. The thing is that nobody's ever built a real excavator. Well, it's not entirely true. There was a scoop on the Surveyor, and there was one on Mars, but those are scientific scoops. They're not like industrial production
Okay.
type machines. Right. And so really nobody's ever designed and built a lunar excavator to function under these conditions. And so we can't just go buy parts. CubeSats, even though they've become a lot more prolific, you can buy stuff off the shelf, but it might not quite be what you want. But there's something for a lot of budgets there, right? And so budget, of course, plays a big role here. And so what we try to do is leverage some of that experience and knowledge from the CubeSat world where we can, right? So from an electronics perspective, for instance, there's a lot of similar components from a control standpoint. But on the other hand, things like motors and actuators, they've been, of course, made and used for, let's say, Mars rovers and things like that. But you can't just buy those off the shelf. Those are custom-made devices that are not easy to do. And so what I like to do is often I like to partner with some companies that have some experience in those places. And of course, they like to hire students and they need more employees. And so it's a good experience for the students, and it is a good experience for the companies as well to get students that then are already experienced in working with them, but also with some of their hardware.
Right. We do the same thing with data science students at our local university. That's a master's degree student session to come on over and work on something cool, and they love it. And this is Jason Kanigan from Cold Star Tech, and I'm excited to share with you a new offer from Cold Star that we are bringing out to help both space founders and venture capitalists who fund space companies. And it's on two levels. The lower level is a VC who is looking at possibly funding a space company, but they just don't get it. Right? And a lot of tech founders want to come out and create some sort of technical capability, but they do not understand business. And so you'll look and you'll go, where's the customer here? Where's the business model? And they'll go, but I want to make rockets or something, right? And it's really cool. Well, that, as we know from the dot-com era, is not a viable business model. And so you bring us in. We've got great technical expertise on the space side, folks who have done this sort of assessment before, like our technical engineering advisor, Dr. Rick Fleeter, myself in the process engineering field, plenty of other people with brains to look at this problem so that you don't have to blow your brains out trying to figure out how to make this work. And on the company side, it's a benefit for them because we will show them the roadmap to how you're going to get funded, how you will want to fund them, what changes to make to get VCs excited about putting money in. And so that's good for you. Right? The second level is at a deeper and higher level at the same time. It is for venture capitalists who have given a seed round to a company, a space company, and that has gone on for a little while, 6 months, a year, something like that. And it is time, as COVID has made it, to double down or get out. Those are pretty much the choices, right? It's time to invest further in a thing we already know, which seems to be the direction VCs are going in right now. They don't seem to want to look at new things or stop, just kill the project. And so the good news is, in that situation, there's a lot more going on. There's more meat for Cold Star experts to get in and analyze, right? You're going to have processes in place, whether they know it or not. We'll be able to flowchart those and maybe accurately document them for the first time so we can get some kind of value chain going in the organization. We'll be able to test whether the leadership is the right group of people or whether you're missing something, the strategic direction, the business model, all this stuff. So if this sounds interesting to you, reach out to us. You can email me at jason@coldstartech.com or just connect with me and message me on LinkedIn. That's probably the best way to do it. And I am excited to talk to you. The kind of transformation that we're able to offer here is beyond anything you'll see out there. And as a VC, this will save you so much time and energy, right? Like if you're a VC and you've got 100 companies to look at, you've got 3 days a year to look at each one maybe, right? That's not really good enough, is it? Wouldn't it be better to have experienced, expert space people who understand space, right? Look at this investment and tell you, here's a grade, right? Here are several grade areas. Is this thing ready to pour gasoline on the fire, or is it just going to go up in smoke? This is Jason Kanigan from Cold Star Tech. Let's get back to the interview. What are you going to do, or what are you doing to mitigate the risk here, I guess, of like this is a learning experience, right? You're gonna over-design the heck out of this robotic scoop or earth mover or something, right? It goes to the moon and it functions in some manner. And we don't, we can only guess, as you've said, right? It'll either perform really well and be overbuilt, or it'll be under the tolerances of what it actually needs and it'll break. Then what? Right? You can't really say, well, okay, send the next one over, right? So what do you do?
Well, that's a great question. So one of the challenges when we deal with call it dirt, the regolith, is that it's a natural material, and that means it's going to vary from place to place. And so even if you simulate something here on Earth with a simulant and all that sort of stuff, what you're going to find locally on the moon or on Mars is not going to be exactly the same. And so you need a factor of safety to deal with the local variation that you're going to see. And so that means that on Earth, when you deal with safety factors, so you just plop some more mass in it, right? You just make a bigger excavator, you put, weld some steel on here, right? So make it stronger. That's not a traditional approach in the aerospace world. The typical idea is there to make it, every gram counts. And that's a challenge when you deal with these kinds of industrial type machines. And so I think one of the big challenges that we have is we really need sort of a paradigm shift in the design of these kinds of aerospace systems, because this is not a science machine. This is an industrial production machine that needs to just do its thing, and it needs to do this repeatedly for a long period of time. And so it does need to be very robust, and it does need to, of course, be cleverly done so that we have redundancy and factor safety where we need it, and in other places where we don't need it, we don't add extra mass. And I don't think that we currently have the answer to all of these questions. This is part of what my research is about, is to figure out where do we need those extra factors of safety, and where can we just use the sort of more traditional aerospace approach, if you will. And where does that break down, right? So that's why we need to test this, and not just for, let's say, 3 days. Oh, this was a great test. Let's test it for 6 months and really see, where does it break down? What kind of wear do we see? Are the materials at all suitable, or do we have to invent a completely new material that may have to work? Right? People are looking at bulk metallic glass that can function under really cold conditions, for instance. So there are different options being explored in that sense. But at the same time, if you look at the plans for SpaceX and Blue Origin and the SLS, just large rockets with large mass volumes. So maybe an extra couple kilograms here and there is not that bad of a thing. Maybe that's okay.
It's just really interesting to think this through, think the problem through, and consider like the problem of digging, that we're so used to. A child knows what this is, right?
Sounds
on Earth,
easy,
terrestrially, right? Yeah. But you've got a much lower gravity, a totally different material, which could be different from one location to another on the moon where you're going. And so even something as simple as scooping, you have to test this for a long time. And so you need access to a low gravity simulator with the right kind of material in it, and temperatures, as you brought up. It's it's a little bit intimidating, actually, to think about it. It's you can't just go down to the corner store or the Radio Shack and get this stuff. So you founded something called the Planetary Surface Technology Development Lab. What is that, and what does it do?
Well, this is kind of the next step, if you will. And so I've been working for a long time and on sort of designing these machines and doing testing in sort of Earth, atmospheric conditions. And so when I started looking at, okay, well, what does it take to get this ready to go to the moon? How do you get this stuff and get it to TRL level 6, which is relevant environment testing, before you send it to space? There weren't a lot of test facilities available that people could go and test their stuff. There's some sandboxes here and there with Lunar Regolith simulants, but not in vacuum, and you couldn't do the temperature simulations, and you can't do the temperature day-night cycles, or they're really small, and so you could only test like a small piece of it. Or NASA has some really giant ones, but obviously it's like $1 million a test, so that's certainly not affordable for startup companies or for universities. And so what I thought there was going to be a need for was a test capability for sort of, let's call them CLPS-sized systems, right? The CLPS is in the Commercial Lunar Payload Services systems that, you know, commercial companies can send cargo to the lunar surface. And so a lot of companies are developing these payloads, but where can you test them? And so the idea of the Planetary Surface Technology Development Test or lab is that we can do a bunch of that testing. And so we can develop the payloads. We have an 1,100 square foot lab where we can go from initial prototyping, 3D printing, just quick iterations, to a sandbox that we have in the lab that is filled with Lunar Regolith simulant, where we can do, it's a 14-foot by 6-foot box, where we can drive around and get some more experience in actually driving this thing around, look at traction. We can, in the future, we can do some gravity offloading, so we can simulate 1/6 gravity by lifting up 5/6 of the weight, and so it only has 1/6 of the weight left on the wheels, basically, so you can look at the traction. And then the next step, right, once you sort of got your design sort of, oh yeah, we think this is pretty good, now you can start doing your space quality testing. And so now you can start simulating the vacuum, the temperatures, and of course the Regolith simulant under vacuum conditions. And one of the funny things is that the presence of atmosphere actually makes the dirt, the soil, behave very differently. Particularly since it's really fine, the air particles actually get trapped in the dust particles. And what's interesting is that at the Lunabotics competition, when you try to refill a hole, it almost behaves like a fluid, because there's so much air trapped in the particles that literally it sloshes until you can get the air removed out of between the particles and that sort of thing. So when there's an atmosphere present, the simulant behaves quite differently than under vacuum conditions, where that wouldn't happen. And so it's very important that you do the next step, testing under real lunar conditions as best as we can simulate them here. And so my lab has now under construction. Was supposed to be delivered here in a week or two, but with the whole virus thing, that's been a little delayed. A dusty thermal vacuum chamber that actually can simulate payloads up to, let's see, I think it's 50 inches wide by 70 inches long and 50 inches tall. It's a rectangular vacuum chamber, and so we'll have lunar dust in there. We can do the vacuum, we can do the liquid nitrogen temperature, so -196 to +200 Celsius on the other end. So we can simulate the day-night cycles. We have the vacuum, only 10 to the -5 torr. Not as good as the moon, but you know, when you have the dust in the vacuum chamber, that's unfortunately not really achievable to go down to 10 to the -12 torr. But that gives us the capability to go all the way from initial prototype testing, rapid prototyping, to testing under atmospheric conditions on the lunar surface, mimic lunar surface in the regolith, to all the way to lunar conditions. And so we can test the whole gamut, the spectrum from TRL 1 to 6, all in this this lab that I'm setting up.
Yeah. Do you intend that to help out to be a revenue generator?
Well, as a university, we're a nonprofit basically, so we're not generating revenue as such, but of course we have to pay people and all that sort of stuff, and I tend to make sure that we can graduate our students. But the goal here, of course, is to train a lot of students in that whole process, and they can then go work elsewhere and you know, hopefully bring some of that work back for us to do testing, of course.
Okay. Good. So great. The capability. It is just so fascinating to think about something that you've known your entire life and then discover that there's this place where it behaves entirely differently and you have to filter it in order to be able to get it close to something that we're used to. So very, very interesting. Let's look at a project. It's called the NASA ESI project that you're the co-principal investigator on. What's being done there and what are you learning?
Well, so the ESI project is an early stage innovation project. And the goal for this particular project is to extract water from what they call hard rock, gypsum in this case, on Mars. And the challenge was to do the hard rock piece of it. Because if you go to New Mexico, the great white sand dunes there, white sands, that's gypsum sand, and you could just scoop it up and put it in a reactor, heat it up, and get the water out there. But on Mars, you might land in a place where you might not have access to already granular materials. Unlike the moon, where everywhere you have that broken up material, on Mars, you don't have that everywhere. But so how would you excavate and extract water from a rock, basically? And
you need dynamite or something. Yeah.
Well, it would work, but it's somehow I'm not sure NASA would appreciate
transporting that on your rockets.
Yeah. Well, it's already a big bomb in a way, but still, transporting dynamite might not be the most effective use of space and mass.
So you need to drill or scrape or something. Yeah.
So that would be the initial thought. But the idea is, again, because we have to do this for multiple years and you have a lot of wear on your system, how could you do that? How can you excavate a rock without having any wear and tear? And so we came up with an idea to use a water jet.
Okay.
And basically, gypsum is very soft rock as far as rocks goes. It's on the lowest end of the Mohs hardness scale. You can essentially scrape it with your nail. It's about 30 megapascals of compressive strength. But that means it's within reach of a water jet, like a regular pressure washer I clean my driveway with, can actually break up gypsum. And so the nice thing about that is that the water impact is actually what breaks the rock. And what I thought was interesting is that so we're trying to extract water, and it is water that does the breaking.
Right.
So I don't care that water breaks in water droplets, right? That doesn't make it's not a problem. So we're using water to make more water anyway. And at the same time, the part that actually breaks the rock, it doesn't wear, right? So we have a pressure jet that shoots out the water. It breaks the gypsum in small particles. So we create a slurry, and that slurry, the water and the particles we can suck up. We can separate the particles from the water, and then the wet particles, the sort of muddy material, goes into an oven, if you will, and then we heat that up. First, we evaporate the liquid water, and then we go heat it up more and more until it's hot enough for the gypsum to actually release its bound water in the crystalline structure. And that's only about 210 degrees Celsius, so it's not that hot actually. But at that temperature, you get 100% of the water out of that rock. And gypsum, like I said, is 20% water by weight. So if you have 1 kilogram of gypsum, you have 200 grams of water that's just in the rock, basically. That's quite a lot. Concrete, you could theoretically do it with concrete, which is what we do in concrete ovens or cement ovens, right? We get the water out of there by heating it up, but that you need much higher temperatures. And there's only about 3% water in concrete typically. So not as efficient, obviously. Not to mention it's harder than gypsum. So gypsum is a really unique combination of having a soft rock with a high percentage of water that's fairly easy to work with. And so that's why we chose gypsum here. And so that's what we're working on.
I think that's some good engineering there, because you don't need the drill bit, which would wear and heat up and need replacing. You do need to bring the oven and energy source and some water to start things off. And I'm mentally, trying to think, like, how much water do you actually need to bring? I ran a metal fab shop for a couple of years back in my hometown, and we had a plasma cutting table, but we would often send stuff out, like custom letters or something like that, to be water jet cut. And so you would use a very fine stream of water, and that will go right through thin metal, for example. And so when you say that, I'm like, yeah, it can, even as a pressure washer type spray, which is quite a larger diameter, let's say, hitting that gypsum, it is going to splatter. You need some kind of way of capturing that, obviously, and then take it off to the oven, and then I guess a condenser or something to pull in the vapor as it comes off. So pretty neat process. I like it. And So as long as your oven and and I guess that comes down to the volume of processing that you want to do at any moment, right? Is the capacity of your oven. So it doesn't need to be huge. You just need to be able to continuously process enough and then feed that water jet so that it can continue making more gypsum splatter with enough water in it, then it is consuming, obviously, with the energy and the water jet itself.
Right.
Really, really interesting to think through that. Thank you, because I've watched a few class presentations. I've interviewed Dr. Daniel Britt that will probably almost certainly have come out by the time this episode does. One or two other folks who were looking at lunar ISRU construction methods and that. And I found out, like, we think concrete is so great here on planet Earth, right? And it's so why not just use that in space, right? Well, it turns out you need water as a major component, and water is kind of scarce in some of these places that we're going, or we need to go get it from somewhere. And second, it has not so great a compressive strength. And I don't know about you, but if meteorites are going to be slamming into the structure that I'm in, or the surface over what I'm under, I don't want it to have a poor compressive strength. So I heard you mention 3D printing around 10 minutes ago. So how does that work? Because I don't imagine that has a lot of compressive strength. Where is 3D printing good for Mars or lunar utilization?
Well, one of the challenges when you make a structure is to use the material for its best properties, if you will. Now, metals are nice because they have sort of the same compressive and tensile strength, but concrete has only compressive strength, but really no tension strength almost, right?
Okay.
So which is why we have rebar in concrete, because the steel part takes care of the tensile strength, whereas the concrete itself is the compressive part.
Okay, so it's the opposite of what I said, which is why you can drop bombs on submarine pens and they're still okay. All right.
That's challenging. If you have a right bomb, that still would work. But anyway, so compressive strength is great for structures, but again, that's Earth thinking. Because when you are in space, I actually don't need a lot of compressive strength because gravity is lower. But what I actually really need is tensile strength, because a structure that I live in needs to, if I don't want to wear a suit, that means it has to be sort of 1 atmosphere pressure. And then, you can go with different mixture ratios. So if I have pure oxygen, I can have a lower pressure. But let's say we have 1 atmosphere pressure. And that doesn't sound like a lot, but when you look at a structure that has to contain 1 atmosphere pressure, you get a lot of tensile strength. And the way we built here on Earth is totally not suitable for containing 1 atmosphere on the inside. It would literally blow up every building that exists here because it's not capable of withstanding 1 atmosphere internal pressure. And so you have to think really differently about how you build when you talk about pressure vessels. It's really that's what we're talking about. And so one of the key components there is you have to generate that tensile strength in the structure to maintain that pressure inside. And so what material could we create that has a high tensile strength? And that's actually very tricky, because on Earth, we would use essentially steel or aluminum or a metal of some sort. And if you think about the space station, that's mostly made out of metal. As well, like aluminum tin cans, as we call it typically. But how would you create that using materials that are there? And so you can scoop up the dust and you could pile it up, and that would be a pretty decent meteorite shield, but it can't handle any tension because it's just sand. Now, you could make some sort of concrete. You can actually make ceramics as well by sintering the material or melting the material. And actually that has pretty decent properties. It's really like ceramic tiles, and we've explored that for the landing pads and things like that. But it's hard to make a structure out of that, right? So making tiles is one thing, but creating a structure that can handle a pressure on the inside is not trivial. And so that's where 3D printing, additive manufacturing sort of can come in, where you could conceive that, say, let's make a titanium powder on the moon or something like that. And then we can additive manufacture, 3D print a titanium structure, for instance. And we can do that. We can do that here on Earth. Right, so rocket nozzles are sometimes 3D printed and things like that. but it's challenging to do to get the right quality that your construction can handle the pressures and temperatures that we're talking about. And so at first, until we learn how to do this, I certainly would not want to live in a structure that we 3D printed. First of all, you need to have a controlled environment, right? When we do 3D printing here on Earth, we have sort of in an oven, we 3D print these structures so we keep make good bonds between the different layers. And I think that's a big challenge to do that on the moon. And so the way I see the additive manufacturing, it's mostly for non-critical structures. And what I mean by that is not pressurized, right? So think about landing pads or berms, walls, roads. You could even sort of see maybe a shed or something like that I park my robot under for protection, but it's not pressurized.
Right.
Right, so that's kind of how I see the initial applications of 3D printing.
Okay, you've got me thinking of pressurized buildings with revolving doors. Like there was a stadium in my hometown, BC Place, and the roof collapsed about 10 years ago. I think it was pressurized on the inside. They lost that, and they had to do something about it. You know, it was like a fabric roof. So that pressure is maintained inside with the revolving doors and that. Also plywood. I wonder how the plywood model would be used here, because you mentioned layers, right? And so plywood gets its strength from having these crossed layers of the fibers. So that's something that I'll be watching for from now on. To see where, if anywhere, you guys go with that. So let's finish up with this then. And we've kind of touched on a part of it here with the question we just answered. What do you believe are the most important next steps for figuring out ISRU for construction of mining on the moon and Mars? Obviously, some sort of 3D printing or something that can handle pressurization so that we don't have to stay in suits all the time. What else?
Well, I mean, you talk about the next steps, but I mean, to me, the first step is to go out there and do it. And so the challenge is that we haven't been back to the surface in a long time. And so first of all, we have to go back and make sure we can do all those things, the basic steps to even just get there. And then the second step is, okay, let's just try out some things, because there's only so much we can really simulate here on Earth.
Right.
And being able to build something and then just test it there. What I mean is build a robot and then test the robot there, make sure it performs the way you think it does, create something, a road, a landing pad, something, and then see how it holds up. And the quality over time, see how the robot functions. Right? All those are the basic first steps, is to learn how to do that. And then scale it up to some bigger things, right? Maybe we actually create now a mining base on the moon. Maybe we actually create some nice roads and we drive over it for a couple of years to see how that holds up. And by doing those kinds of things, we'll learn how to do that properly. And so the way I kind of envision this developing is kind of an Arctic-style research base that's focused on ISRU, learning how to use the local materials to build things, right? So we start out with the oxygen and the ice, the hydrogen and the oxygen, and then we start to learn how to do the metals. When you extract the oxygen from the Lunar Regolith, you're essentially left with a waste product that has a lot of metal in it. And so, maybe we can start using those metals for something like that. The challenge that I see coming down the line with that is, how do you create a let's call it a half product, something in between that we could use for, let's say, additive manufacturing. And so I can't just scoop up some lunar dust and when I extract the oxygen have pure titanium left. It's a mixture of all sorts of things. And so how from that do I create a quality product that can handle tension to the level that we need? And so how does that product vary, right? So on Earth, we have very complicated process control steps in place to make sure that, like, if I put my titanium powder in my printer, it's 99.99% titanium oxide. It's the powder stuff. And so there's a complicated industry behind that creates those kind of things. And it's going to be a while before we get to that level of quality control on the lunar surface. And to me, that lunar base that focuses on using the local materials is going to learn and really figure out how we can use that local material. How can we separate it? How can we create that high quality material that allows us to do that more advanced manufacturing that we'd like to do? And so at the beginning, we want to just use whatever's there, right, without doing much processing and without a lot of energy. So it's very useful as it is. But that next step, we need more energy. We need the research going on on site locally, and to really try to understand how that works.
Yeah, this is a tough thing because it is like going into an Arctic or an Antarctic desert, like you say. There's no wood, there's no fuel source in that sense. We've got to pull it from somewhere else. Metals
no Home
rare.
Depot or McMaster car.
And these, we can't just ship it to the Great Lakes and have something done with it in a foundry or something right in that region. So it is a lot tougher. Plus, there has got to be a reason, and this is, I think, the biggest challenge, for us to have a long-term human presence there. For these years that you require for building a road and seeing what happens, or a landing pad and seeing what happens, and getting this iterative process going. So I think that's the next biggest challenge. Paul, where can people go to find out more about you and the lab and what you're doing?
Well, so like I said, I'm a professor at Michigan Tech, and so you can contact me at Michigan Tech. You can search for my name, but also you can email me there, pjvansus@mtu.edu, and I assume you can share that information with interested audience members. And so email is probably the easiest way to get a hold of me. If you have any questions, or you'd like to discuss how testing under lunar conditions or things like that, I'm happy to collaborate in all of those kinds of things. And so, yeah, email is the best way to get a hold of me. We're working on a website. It's not up yet, mostly because we don't have any pictures of, let's say, the vacuum chamber yet, because it's not delivered yet. I do have drawings of all of that stuff and descriptions of the capabilities, but we haven't put it online yet because it's not operational as of yet. But depending on how long this virus situation lasts, I hope to be up and running by early summer in this case. And so I'd love to hear from you, love to talk to what people's plans are, and see how we can help you out with those things.
Right on. Dr. Paul Van Susante, thanks for being here today.
Thank you, Jason. Glad to be here.
This is Jason Kanigan from Cold Star Tech. Thanks a lot for listening to this episode. I hope you enjoyed it. If you do want to get email notifications of upcoming episodes or episodes that have just been released, and maybe a little news sprinkled in here and there, you can sign up for email notifications at coldstartech.com/MSB. That's short for Make Space Boring. That's another little show that I do. It's once, twice, 3 times a week, something like that. Anytime there's news or an update on who I'm meeting and what I'm studying in the space field. So you can go check that out. On the YouTube channel, I can do something that I cannot do on Anchor for the audio only side of things. The YouTube channel allows me to have playlists, and so you might want to go to the channel, the Cold Star Tech channel, and check out those playlists, because you will find you can go down a rabbit hole basically into several areas like space law and policy, small sats, and I think that's a lot easier than trying to scroll through 130 episodes or something like that, looking for the thing that you want. So I recommend going and checking that out. And remember, if you're ready to take your space business to the next level, or you're a VC looking for deep and very valuable insight into a space company you're looking at investing in or investing further in, come and talk to us. Thanks for listening.